So let's see what we've done so far. First, we had an introduction to linear systems and Fourier transforms. We learned about the Green's method. That tells us if I know the Green's function or the impulse response, I know everything I need to know about that linear system. The output to any input will be a convolution between the input and that impulse response. Then we found that Fourier transforms are very efficient tools for linear systems because that convolution, for instance, can be written as a product in the frequency domain. And to make it even easier, we went through several properties of the Fourier transform. The shift theorem. If I shift the function, then I get the Fourier transform as if it's not shifted except for a modulation here, a sinusoid, a complex exponential, whatever you want to call it. Then we had the similarity, the scaling theorem, that if one function gets fat in one domain, it becomes skinny in the other domain. That was good. The conservation of energy, Parseval's theorem. And then I think we showed that. The convolution theorem and the correlation theorem. Finally, we showed that the differentiation of a function gives you a Fourier transform that's the same Fourier transform as the undifferentiated function, except for multiplication with I omega, or minus I omega, depending on what your convention is. And the same thing happens in space. The del operator, take the Fourier transform of that, is ik times the Fourier transform of the function. So this was a quick exercise where we said, what happens if I have my wave equation for one component of the electric field, and I have this weird source that is a delta function in x, so it only exists here at the origin, let's say, as a wall, infinite wall at x equals 0. What would be the waves coming out of that source? So we solved the wave equation. How did we do it? We put a delta function here in x. We took the Fourier transform of that, and we remember that Fourier transform of a delta function, infinitely skinny thing, gives you infinitely broad thing. That means it gives you 1. So we have this equation. The del function gives you k squared, and since we are on x, we called it kx squared. Beta naught, keep in mind, is a material property. In this case, we're in vacuum, so it's just omega over c. If we were somewhere else in glass, that would be n times that, right? So the electric field, exactly how we did with the differential equation for the mx 2 dots plus blah blah blah, the equation of motion, we got the same thing. E as a function of kx is immediately this over this. And this is actually the solution in the spatial frequency domain for the field coming out of that infinitely broad wall that exists at x equals 0. In order to find it in the spatial domain, we need to take the Fourier transform of this with respect to kx. And there are other ways to do it, or just look in the table. One way to think of it is that this is kind of a Lorentzian. If you put this kx as, you put the I inside. So when you write the exponential, the Fourier transform of this Lorentzian gives you an exponential that also has I in it. So we simply got something that looks like this. E of x is actually e to the minus beta naught x, and this is just a constant. It's important constant if you look at the frequency at the omega dependence, but spatially there is nothing in the amplitude that varies with x. That means this is a wavefront that propagates along x without any attenuation. It's infinitely broad. Only the phase is changing as I propagate along x, is changing as beta naught x. Every distance 1 over beta naught, I get 2 pi phase. All right? So that's a plane wave. The reason we write it as a dot product between k vector and r is because whenever my system of reference is not aligned with the direction of propagation. Okay? So this is the one-dimensional solution of the wave equation. I know you knew that. Should we do the spherical wave quickly, or what do you think? Let's do it. What the hell? So here's the problem. I have a point source here. An infinitely small point source by itself in the universe emitting light. That's the problem. We want to know the field that's coming out of that. Well, we don't know anything. I was going to do this, but that assumes I know it's going to be a spherical wave. So we don't know that. Let's say it's Laplacian of u of r and omega plus, in vacuum, again, is beta naught u of r and omega. And now here, I have the same thing, except that my delta function now is in 3 dimensions. Okay, in 1 dimension means an infinite wall at x equals 0. A delta function in 3 dimensions means a dot somewhere suspended. Since it's of r, it means it's in the origin. X, Y, Z. How do we do this? Same way, right? Okay, so let's take the Fourier transform. Now, we're in 3D, remember, we're not in 1D anymore. So I have 1k vector times ik vector times u of k, let's say vector, and omega. We're going to find out that it doesn't depend on the direction of k, it only depends on the modulus. Why? Because we're in free space. Going this direction or this direction or this direction doesn't make any difference. But let's keep it vector for now. Let's assume we don't know. Beta naught squared of u times u of k and omega equals a of omega times Fourier transform of delta 1. Delta function in 1 dimension and the delta function in 3 dimensions, they are different. Why? Because in 1D, integral of delta of x dx is 1. In 3D, integral of delta of r d3r is 1. So for one thing, they have totally different units. Okay? So that's what we mean by this. We mean the actual 3D delta function. That has the Fourier transform equal 1, which now means constant everywhere in space. Not just a wall, not just a line, it's everywhere is constant. Boom, once I know this, the solution right away is u of k and omega is what? A of omega over beta naught squared minus k naught squared. Oops, why k naught? K. Again, don't get confused. Beta naught is omega over c, property of the vacuum or of the medium. K, frequency domain. Okay, this u is a function of this. So you see right away that actually it only depends on the product of k with itself, which is the modulus square, rather than the direction. So I can remove this. What's the Fourier transform of this? You see how this is different from the 1D? Very similar. Is kx and omega, right? Is a of omega over beta naught squared minus kx squared. That's all the difference. So, do you have any idea what would be the Fourier transform of this? It's not that trivial, actually. I mean, it's not, unless you've seen it before, you don't know it. We know the result is going to be the spherical wave. But I don't want you to get surprised. The Fourier transform of 1D gave us 1 e to the I beta naught x over beta naught. The 3D is going to give us u of r, so this is the final solution in 3D, is a of omega, which is irrelevant. It's going to be e to the I k, so this k, I'm sorry, beta naught. So you see, I'm taking the Fourier transform, I get rid of k, everything should be r now. I'm going back to space. So it's, again, it's beta naught times r, right? Not x anymore, and also over r. There's no magic. If you work it out, if you look in a book with a 3D Fourier transform of spherically symmetric functions, it's interesting. But anyway, this is the result. You know what the Fourier transform of spherically symmetric functions? What it comes down to? So functions that don't depend on x and y depend only on the x squared plus y squared plus z squared. The integrals, using this symmetry, the integrals from 3D become 1D, right? They only depend on r. And it turns out something very funny. The kernel of the Fourier integral goes from e to the I kx x plus ky y plus kzz, which is the definition. You replace that with the sign of kx over k. The sink becomes your new... Okay, let me write it down.
When do we have an I in 3D case?
Of course, yeah. Did I miss it?
I think it's
Here.
to the beta not R without I.
Here?
Yeah.
This is an I. You mean this one?
Yeah.
Yeah, like this is correct?
Your brother's note, there's no I there.
Oh, really? My notes are wrong then. Okay, so there should be an I here. Okay, I was saying how the Fourier transform becomes of f of r. We write it as a Fourier transform f of k in 3D e to the I k times r d3k. If f is only a function of the modulus of r, basically this becomes very nice or interesting. Is the Fourier transform of k, so the Fourier transform is also only dependent on the modulus. Okay, no vector here, and it's something like this: sine of kr over k r times r squared dr. So it becomes a 1D integral over 3D function, right? And it happens that it's actually the sink is the new basis for that. Anyway, just wanted to let you know. So that, if you know that, then you can do the Fourier transform of this and you end up with that. What's the difference? Big difference. This has no x, no spatial dependence in the amplitude. This does. Okay, so that means if I have a point source here and I let it emit in free space, there will be a phase change where beta naught also tells you how fast the phase is changing. But also, the amplitude drops down as of 1 over r. The intensity will drop down as 1 over r squared, just because getting a bigger and bigger circle or sphere, for the power to conserve, the amplitude in it has to go down at 1 over r rate. Okay? Do you have any questions about this whole thing? These are well-known results. I know you knew them. I just wanted to connect with our Fourier properties. You believe me? Okay then. Okay, let's move on. So, where did you say I was missing an I? Which note? Where was the I missing?
In the solution for 3D case, the point source. Yeah, but from your course note in the groundwork, in the easy by 64, there's no I.
Okay, let's not talk about the course now. Something that everybody understands. So he took my course this semester and I had typos in there. Thank you for revealing that to everybody. Okay, so this is the one solution to the wave equation. One important thing to realize is that here, the Fourier transform of this simple equation here gives you minus k squared plus beta squared equals 0. In other words, the modulus of the wave vector, k, equals either plus or minus beta, You remember those counter-propagating wave vectors that we started with? Okay, if you only take the positive part of it, is beta or omega over c in vacuum, or n times omega over c in another homogeneous medium. This is called dispersion relation. Is the simplest dispersion relation, right? And for homogeneous media. So it tells you that basically, no matter how the vector is oriented, the modulus should always be material dependent. It's set by the material. So I know all of you knew that the modulus of the wave vector is 2 pi over lambda or omega over c and so on. But this is where it's coming from. Without prior knowledge, from Helmholtz equation, you take the Fourier transfer, you get k squared equals beta squared. Beta is a material property, k is the modulus of the wave vector. That's it.
Does this say, and this is the problem with me reading, does it say omega over c equals n times omega over c?
Yeah, it shouldn't be equal, but what I mean is in media that are not vacuum, like media with n different from 1, you add an n in here. Okay? So I can put it here in general. For vacuum, n equals 1. Now I made it the other way around. Okay. Is that good? Yeah? Okay. Let's get more complicated then. You remember the conductivity part, sigma E, those currents, the one that had I in it, and we had the parenthesis about irreversible processes and so on. Basically, you can think of n as the real part n prime of omega plus I n double prime of omega. So, which means that if you multiply n with your k naught, you will get a real part and an imaginary part of k, which if you replace that in the plane wave, you will get one amplitude modulation right here. So you see the I from the k double prime with the I from the plane wave. So we had something like e to the I k r. Right? If I plug this in here, I'll get an I from here with an I from here. I get e to the minus I k prime r times e to the, or plus, and then e to the minus k double prime r. So basically this is amplitude part and this is the phase part. Right? So what does that mean? It means that in a material with conductivity, like metal, there is some attenuation due to the imaginary part of the refractive index. And that's exactly why we cannot see very well through metals. That's why they are very opaque. The other part, the refraction part, is this one right here. That's something to do with the real part of the refractive index. Okay? So you see, if you start with a plane wave, you are going to have a phase change and then an attenuation. And that's basically something to do with the Lambert-Beer's law for absorption right here. Okay? Are we okay? So nothing too fancy. Now let's go to k omega representation. We already did that to get the plane waves and the spherical wave. So we went from space-time r and t, we went to r and omega. We derived the Helmholtz equation. That's what the Helmholtz equation does. Basically, Helmholtz equation tells you how to solve problems if your light is not monochromatic or cannot be approximated by monochromatic, but it actually has a broad spectrum. So you go to omega domain, solve for each omega, and then sum up the results if you want to go back to time domain. K omega representation is similar for the spatial domain. So what happens now if instead of a single plane wave, I have a bunch of plane waves? In other words, I have a beam. Right? I take the light from my laser, I focus it down, or I just use it as is. Oh, there we go. This is not a plane wave. Why? If it were a plane wave, it would be everywhere, right? So we know it's not a plane wave. Sometimes we don't care. Sometimes the fact that it's fairly uniform over 1 centimeter, that's good enough. Why? Maybe because my detector is much smaller than that. So I can approximate it that way. But sometimes that's not good. So it means I need to solve for each of these directions that makes up my beam, right? For each k component. So how do we do that mathematically? Well, we use this again. So we'll get the version of the Maxwell's equations in the k omega domain. So you see the curl right here gives you k cross, similar k cross h. Now here you have omega, all the derivatives disappeared. And you get also something very interesting. K dot d equals 0. What does that mean? They are perpendicular, right? And we also get k dot b perpendicular. So I'm sure all of you knew this. Usually what we say is that k, e, and h are all mutually perpendicular. Actually, in reality, k, d, and h, and if you have magnetic materials, k, d, and b are actually mutually perpendicular. But in crystals that we use every day, actually, k, d, and h are mutually perpendicular. I think I have a, yeah. It's something to do with the fact that epsilon is a matrix in the general case, and d is not necessarily parallel to e. Okay? So e could be like this. That's okay. So if somebody's telling you, oh, e is not perpendicular to my k, that's okay. It can happen in crystals, in anisotropy materials. Okay? So again, we got these orthogonality relations just bringing the Maxwell's equations in k omega. So how do I think of the problem? Basically, if you give me a k, if you give me this plane wave going along this direction, this is what's going to happen. This is the k. I have maybe two components of the e, two components of the d, two components of the h, two components of the d, of the b. They are all related this way. That's it. Okay? Do you have any questions about this? So this is basically very simply showing you that light is a transverse wave without any magic. Right? You can define some impedance that by definition looks like this.
B and H, do they need to be parallel?
I ignore the, in general it can be, you can have an isotropy in the mu. So if that happens, then your material is called bi-anisotropic. I never dealt with that in real life, but it exists. So if your mu, the magnetic response, is anisotropic, then H and B are not necessarily parallel. But in most optics labs, we don't really worry about magnetic response. Okay? So that's why I ignored it here. Most of the time you have K, H, and D that are mutually perpendicular. I mean, this is just a matter of definition. This is the impedance. It has a fixed value for vacuum that is 370 something ohms. That's the square root of mu over epsilon. If you have conductivity, this has to be corrected like this. In optics, we don't use impedance all that much, but in electromagnetics, in lower frequency electromagnetics, is a very common thing to do. Anyway, just a definition. Now, here's a question. If I have a broad bandwidth of my light, how do I define the velocity? Especially when I have a medium that is dispersive. And what we mean by that, I have a refractive index that depends on omega. And I know that the velocity depends on n. The higher n, the slower the light is. But now, n depends on omega. So that means if I send a pack of wavelengths, like a short pulse has to have a broad distribution of frequencies, right? What do I call velocity? You see, it gets a little complicated. I have a bunch of frequencies. The speed of each frequency is different from one another in dispersive media like this. Okay, you already know these things. So there are several types of velocities we can define. One is the phase velocity. That is simply V is omega over k, end of story. The bigger question is, how does my field behave on average, as an ensemble, as a group? And it turns out we can define the velocity of the whole package, okay, as I'm trying to show in here. So in a way, you can think of a signal as an envelope and then a carrier, okay, or a high frequency modulation. So sometimes the envelope and the carrier move together. When does that happen? Non-dispersive media. Only then do we have these phase and group velocities go together. Now, if you put this through a dispersive medium, what's going to happen is that omega 1 is going to have a velocity, omega 2 a different velocity. They're going to start slipping from each other. They're going to be different. Long story short, the phase velocity can be easily defined like this. Imagine I have an average velocity omega between the angular brackets. I have an average k, which means this. So I know this beam has some angular spread, has a spreading case, but I can pretty well define an average k, right? In other words, the spreading k is smaller than the main k. Okay, so this direction is what I call the average k. So this is the phase in space and time. If I do a differential of this phase and I say this is constant, so in other words the differential goes to 0, I can define dz at dt as omega over k. And that is what we call phase velocity. But this is actually just the 0th order term in something more complicated, if I have dispersion. If I have dispersion, in other words, dn at d omega is non-zero, then what I call group velocity is actually a correction over the phase velocity. It's different from the phase velocity. Actually, it's the derivative of omega with respect to k. Okay, you can think of these as different terms in a series, in a Taylor series. So you see right away, if the dispersion goes to 0, like in vacuum, group and phase are the same. Question for you: can the phase velocity be higher than c? Yes, no problem. Can the group velocity be higher than c? Well, let me ask you this more specifically. Can this derivative be negative? When does that happen? We didn't do this, but basically, from the solution x of omega that we just found in the equation of motion for electron in the nucleus, if you add all the optical properties of the material from the microscopic picture, electron on a spring, to the macroscopic picture, from x of omega, you can get basically n prime of omega and n double prime of omega. I told you that this is already a complex quantity because the loss is out of phase by power over 2. It turns out you can build n prime, the real part of the refractive index, and the imaginary part of the refractive index straight from here. And they look like this. At the resonance, remember the resonance of the spring, there is an absorption line that looks like this. Nothing surprising. Oops. I keep forgetting that you always have to draw the line and then the center frequency. Right, so that's where the spring resonates. That's where it absorbs most of your energy. Same thing, that's where you have a dipole active mode in your atom. That's going to absorb most of your light. Okay, nothing special. This is a Lorentzian function around the absorption. And this is n double prime. But let's now draw n prime. And you have to believe me that it looks like this. It goes up. Let's do a different color. It goes up here. It goes up here. So you see it increases with frequency. It increases with frequencies, both to the left and the right of the resonance. But in between actually does this weird stuff. So you see, dn at the omega positive, dn at the omega positive, but here is negative. Which means that this can be negative around a resonance. Which means that group velocity is greater than c at around the resonant frequency. And there was a Nature paper that made a big splash, including in the Romanian news, my home country, because one of the authors was Romanian, and the title was, in the Romanian news, "The Romanian who defeated Einstein." And of course that was wrong. It was just a misunderstanding. It was the first realization, an experimental realization of this sort, where you prepare your pulses such that it hits the material at resonance. Actually, it's a double pulse. It was a complicated experiment, but they achieved group velocity that was 300 times higher than c. So that was interesting. The simple idea is kind of like this. If you have a, I don't need this. If you have a pulse and you pass it through a gain medium, so this can amplify stuff. The leading edge of the pulse, which is very low power, once it hits the medium, it's going to get amplified. And then you have to saturate the gain such that when the big part of the pulse comes in, actually gets attenuated. So you see, it's as if you get the pulse much faster on the other side, but in fact, it's not the same pulse. It's the leading edge of the pulse that gets amplified, and then the main pulse, the peak of the pulse, got attenuated. So that overall, if you measure, it looks like the group velocity is much higher than c. But this is not contradicting what Einstein said, because there is no way I can encode any information in this, in the main part of the pulse that will come out faster, because we're talking about different signals. So there is no information in here that will come out faster here. This will be slower than c. It just looks that it's faster. The group velocity is higher, but the signal velocity is lower than c. Okay, so that's the third kind of velocity, which is called signal velocity, which is the ability to send information, is the speed at which you can send information. So in this case, you cannot send information faster than c, just because you're amplifying something that basically was very low power before. Anyway, so this is kind of a parenthesis, but try to kind of think about this. When you have the dispersive material, defining the speeds gets a little tricky. You need to be careful. Okay? Basically, the frequency starts to slip away from one another. They go with different velocities. They don't act as a group. One gets faster, one gets slower, so they spread. That's the meaning of this. Okay. I'm not going to go through this derivation, but I think it's interesting. You can show rigorously that actually the group velocity is the energy velocity. Okay, let me say that one more time. The group velocity that we just defined, we didn't talk about energy at all. What happens to the energy? you can prove that actually the velocity at which the energy is delivered by the light is exactly the group velocity. Okay? So the energy velocity is defined by the Poynting vector. You define the energy density. And you go through all these steps and you're going to find exactly this. That they are equal. So, yes?
For the left-handed materials, actually. For the left-handed materials.
Oh, man. Okay.
Is it the same or like?
If the energy velocity and the group velocity are the same?
Yeah, I mean, they have to be like opposite.
Should ask somebody better at left-handed materials. I don't know. You think it's different? I don't know. Yeah.
So actually, different material started from the first paper from Pisagor, 1968.
Okay.
I mean, that's kind of made the whole world of metamaterial, including negative reactive index.
Okay.
And recently, I think he published a paper which exactly talks about his problem. And according to his paper, actually it travels in opposite direction in left-handed medium. So travels backward.
The opposite compared to what?
Compared to right-handed medium in normal case.
Okay, but are they the same in value? The modulus is the same?
Because wave
The
propagation is opposite to the energy direction. Wave propagation direction is opposite to the direction of energy flow. So for the left hand, that's why.
Oh, so the group velocity and the energy velocity go.
Yeah.
That sounds interesting. I need to read more on that. I'm sorry, I'm not a negative material guy. It sounds possible, it's very weird. The reflection is easier to see. I'm not sure about the group velocity, but I believe you. So why don't you make a poster out of it and teach us how it is? Huh?
Sure.
That would be nice. Okay. Okay, quickly. Everybody knows Fresnel's equations. But let's see how you formulate the problem. I'm sure you can work out the math. But basically, I have this interface between two media, N1 and N2. I have an incident wave vector here. I would like to know first, so that means if I draw only one wave vector, it means that I'm talking about the plane wave. Right? The question is, what happens to this plane wave going in? What's the angle of refraction? And also, how much of the field will go into the other material? How much goes into this material? I want to know everything. If you give me these components of the electric field, this direction of propagation at this interface, and you give me the refractive indices, I should be able to work out everything. All the components of the electric field in that medium, in this medium, their phases, their relative amplitudes, everything. And the weird case is when nothing goes through or nothing gets reflected. There are two strange cases that we're going to discuss now. Okay, so remember we go back to our boundary conditions. The tangential fields are conserved. The normal inductions are conserved, B's and B's. And we threw away the currents and the free charge density. And these are the Maxwell's equations in K omega. Okay, it's nice to work in K's because we're talking about plane waves, right? So look how nice this is. E and H are connected directly. If you give me the components of K's and the components of E, I can tell you what the H is with some constant. Okay, oops. So it turns out that the problem naturally breaks into two situations. I don't think I have the proof here, but it naturally comes out. If you look at all the components, if you work out the curl, you're going to see that the problem appears at two different problems. It breaks down into two. One, when the electric field is perpendicular to this plane. In other words, my K comes in and the E is perpendicular this way. That is called transverse electric. For obvious reasons, this E is transverse to this plane. And the other one, when H is perpendicular. H perpendicular means E is in the plane. Okay, so it's in the plane X and Z, it has components in both X and Z. This has only, the TE has only components in Y. Are you with me? TE is this one. TM is this one. H is perpendicular, E is in the plane. And there is no magic, there is no assumption from my part. This comes out naturally from the equations. It breaks into two equations, but I don't think I have them here. Okay, so let's study first the transverse electric. Well, the electric field is here. This is the interface. That means the transverse electric is in the plane. That means that's continuous. So the incident component plus the reflected component has to be equal to the transmitted component. Oops, the wrong way. Right? If this is the E coming out of the plane, that is the tangential part. Right? It's in the plane. So the tangential part in this field has to be equal to the tangential part in this field. So here I have one component from the incident, one component from the reflection. And in field in the medium 2, I only have the transmission. That's why we write it like this. Same thing, H incident plus reflected has to be equal to the transmitted one. And now we plug everything in, and basically you end up with this. Looks familiar? Right? So that's the Snell's law that you can prove in many different ways, but that's nice how it comes out of the Maxwell's equations. Do you know another way to prove Snell's law? Huygens? Phase matching? Well, this is kind of what we're doing here with the phase matching. The K's, yeah. But you know, you can start with the Fermat's principle, which is saying that the light travels across a path of minimum time. If you take a point in medium 1, a point in medium 2, you write the path with a random point in the middle here that you don't know exactly where it is. And once you minimize the problem, it actually comes out to be at the Snell's law. It's the problem of Eve drowning and Bob running to save her, right? You know this problem? Okay, so Eve is here, swimming with velocity 1, and Bob can actually, no, she's not swimming, I'm sorry, she's just drowning. So she's she's stable right here. But now Bob has two kinds of velocities. One in this one that he can run with velocity v1, and he can swim with velocity v2. Question is, how should he run and then swim to get here in the minimum time? Yeah.
Well, you can make an equation, you can minimize the time, you can take the shortest path time-wise. So
Yeah, not the shortest, yeah, I know what you mean, shortest time. Okay, so this is Fermat's principle. Okay, you have refractive index n1 here that gives you velocity v1, refractive index n2 here. And light knows by default how to go. That's kind of nice. Anyway, so it gives this, I'm sure everybody knew that one. The z component of the vector, so in other words, the reflected component of the k vector normal to the interface is minus the one that comes in. That's kind of like bouncing a ball at the wall. Okay? The normal component in an elastic, perfectly elastic interaction, normal component is the same, it's conserved. Okay. And nothing happens to the tangential component when you throw the ball at the wall or when you play billiards, if your billiard is ideal. Anyway, so that's how the Snell's law comes in. More interestingly, if you write the ratio of, remember our E was this way. So this was the only component of E, transverse electric. I want to know the ratio between the reflected versus the incident, right? That's how it looks like. If I want to know the transmission, it's the second equation. And keep in mind, this is in the fields. If I want to know in terms of power, I need to square this. Okay? But this is all you need to know, and this is how I remember the Fresnel's law without all the angles and stuff. If you plug in the angles, it gets a little trigonometric, but basically it's like this. So the Z component incident minus the Z component transmitted over over the sum, and the transmission was 2 times kz transmitted over the sum. It looks similar to the equations in mechanics for momentum conservation, in the ball at the wall kind of a thing. Okay? So this tells you everything you need to know. The TM mode goes the same way, except that now everything is in H. It's much nicer to work only with the H component because you have only one. The E component has 2, right? The E component will be like this. It has a little bit of this and a little bit of that. So if we work out in H, this is what you get. So it looks similar. I like it in this form because I see the similarity with the TE, right? So it's a sum difference over some sum, and this is twice one component of the K over the sum, except that now the K's have to be normalized by epsilon or n squared. You see? So this is not H, it's n. I'm sorry about that. The reason we have epsilon there is because we were talking about H's and not E's. And again, you can plug in the angles, right? The component of the Z, you need to project that K over the Z. It gives you some angles. Okay? What do you think so far? If you ever need to calculate something like this, I think you have everything you need here. Conservation of energy in both cases is that something weird with this. I think it should be R, right? So the reflection coefficient squared, both in TE and TM, plus the transmission coefficient squared should be 1. That means the power I come in is split in transmission and reflection. If I add those up, I should recover what I put in. Okay, so these are the strange cases that I mentioned in the beginning. And the reason I wanted to talk about this is because total internal reflection is a way to kind of get to small scales in microscopy. And let's see what happens. Total internal reflection means that the transmission is 0. In other words, if I look at my oops, the wrong way. If I look here, this component should be 0. Okay, I thought it was an easy way to see it, but it's not. So here's the problem. If you write kz, the transmitted component of the K, which is kind of like this, right? This is my interface. This is the reflected component. And this is the Z. K incident, K transmitted, K reflected. Come on. N1 here, N2 here. The transmitted component of the K vector gets closer to the normal if N2 is larger than N1. And it tilts away from the normal if it's the other way around. You see it? So if this is higher, if I come in at this angle, the angle of transmitted angle will be smaller. The other way around, if this is smaller, it's going to go away. So you see physically there is a point at some angle, if I increase this incident angle, where actually this is going in the plane. It's transmitted at 90 degrees. Well, it turns out you can get that straight from the Maxwell's equations, the way I showed it earlier. But let's take a look at this. If kz transmitted is a square root of kt squared minus kxt squared, the x component of the t. In other words, I decompose this like this and like that. There is a solution for this square root to be 0. The condition for that is that n2 is actually smaller than n1. You see, if n2 is bigger than n1, I don't get the solution for the angle. That's how you see it mathematically. Okay? In other words, oh, that's why I couldn't see, because I was looking at the reflection coefficients in amplitudes. So you see, the reflection coefficient is not 0. I mean, it's not 1. It's complex. Modulus is 1, but it has a phase. Okay, let me say that one more time. The power reflection coefficient, in other words, the modulus square of this guy is 1. That means total power is reflected. But actually the field has a phase change. You see what that means? It's as if I'm coming incident here, all my light gets reflected, except that as if the light passed some time in the other medium and then came out, with some time delay. As if it explored a little bit the other medium and then came out. That's just a kind of a picture. Don't take it literally. Now, what happens on this other side? What do you think? This transmitted side. Well? Huh? Okay, so what does it mean? What does that mean? Well, if my kzt is actually purely imaginary, which we have here, that means when I plug this in my plane wave, I have e to the I kzt means I modulus of kzt times z is actually e to the minus something alpha z. You with me? So what it means is that on this side, the field decays exponentially. Exponentially means very fast. How fast? Well, we can call this kind of a length scale. It's of the order of the wavelength. Again, this is not power. It's fields. The entire power, we recover it in reflection. The field decays a little bit in the other medium. So that goes with my picture of exploring a little bit the other medium and then coming out. And this is further supported if you come with the fiber optic or something on this side, very close to this surface, then you are going to get some power in. That is called frustrated total internal reflection. So it's as if there is light sitting there, it's not propagating. Again, 100% of the power is in reflected, but there is some field there, just sitting there. If you come close enough, you change the boundary conditions, and then you start coupling some of this light in here. Where's that power coming from? Well, the reflected light has to go down. And believe it or not, this is an established microscopy technique working on this. Basically, you send light this way, totally internally reflected. You have your cells here, and most of the time it works in fluorescence. You use this light, you use the evanescent light as excitation. Why? Because it gives you a very shallow depth here. So I'm exciting only a layer that's a fraction of a wavelength from the surface. But that's enough to produce fluorescence, and you get a lot of benefits. First, you get zero background. Okay, there is no excitation coming in, so that's zero background. But most importantly, you get you excite only a very shallow distance from the surface. So that's used, for instance, to look at the membranes that sit on the cell membranes that sit on the cover slide. Okay, 200 nanometers, 100 nanometers from the surface. So very powerful stuff is called TIRF, total internal reflection fluorescence microscopy. Are we clear on this? Okay. All right. But there is the opposite thing. Oh, by the way, I can get total internal reflection with TM polarization just as well. Okay, polarization doesn't matter. I can always find a total internal reflection angle, provided that refractive index 2 is lower than refractive index 1. Very important. What's different is that this phase shift, that phi TM, is different. But when you do fluorescence, you don't care about that. You know one early application, maybe 100 years old application of these phase shifts? In case you're wondering what is that good for. So smart people realize that, well, if this is a piece of glass sitting in air and I'm sending light this way and so on, if I get phi here and then plus this phi, I get 2 phi and then 3 phi and so on. I'm adding these phase shifts. I can play with the polarization. Okay, you know I can go from linear polarization to circular polarization to any elliptical state if I have control over the phi of TM versus the phi of TE. That's a little bit beyond what we've done today, but you can go tune the polarization of your light, in other words, the trajectory of the electric field from circle to an ellipse to a line, by playing with the relative phase shifts between X component and the Y component. If you ever played with the inputs of an oscilloscope, X and Y, and you played with the phase delays between the two and the amplitudes, you get weird shapes on the screen. That's the same problem. So people realize that, well, I can put the light in here, and through total internal reflection I get the phi, and then 2 phi, and so on. And these phi's are different for TE and TM, as we just proved. This phi is different for TM than for TE. So they made wave plates through total internal reflection. A wave plate is this device that changes the polarization. Anyway, that's a parenthesis. What I want you to realize is this, what it means to have an evanescent field. It's a field that decays exponentially. That means very fast in the other medium of a scale that's the inverse of kZt. Since k is inverse wavelength, kind of, it's of that scale. Okay? We're talking hundreds of nanometers or so. And you have a knob to tune it with, depending on the refractive index. Okay? Yeah.
Why surf doesn't have any autofluorescence? Why don't they get autofluorescence? You mentioned.
The excitation is very shallow, right? So it doesn't propagate in the medium.
But still, you're getting inside the cell, right? So.
Oh, why isn't the scattered light act as another? So why isn't the cell acting as a?
Because you mentioned if you put in the fiber close, you're getting some of the light. So
yes.
The cell is going to work like that, right?
Yeah, probably there is some effect in there, but I think it's very, very small. So you're talking about the scattering from the cell, maybe sending light up, right? And that excites some other fluorescence. That's what you're saying, right?
Even the cells can't produce some fluorescence, or the media, the part that still the light goes a little bit inside, right?
Okay, so let me see if I understand correctly. You are saying this. This is total internal reflection. I have a cell here, let's say only one. You're saying my cell acts like your fiber that you showed us a minute ago, and is going to suck some of this power and is going to scatter it in here, right? Why is it that this scattered light is not going to excite fluorescence here and then mess up my shallow depth of field? And the quick answer to that is that the scattered light, the amplitude of the scattered light is much less than the amplitude of the initial field, just because the cells are very weak scatterers. So probably what you're saying happens, but compared to the original excitation, is probably orders of magnitude below. So for the most part, what you get is actually this nice fluorescent sheet from very, very narrow, a narrow layer. Okay? How is everybody? Ready for break? Not yet, no. Just kidding. We have the opposite case of, so we talked about maximum transmission, maximum reflection, no transmission. How about the opposite way? Can we have maximum transmission, no reflection? The answer is yes. That is called Brewster transmission, or transmission at Brewster angle. Let's see how it works. If you have in the TE mode, here's getting interesting with the two polarizations. If I'm demanding that the reflection is 0 in the TE mode, it's going to give me that these two components of K, the incident and transmission, are equal, which basically means that the media are the same. So that's the trivial solution. It means there is no interface. Okay? Obviously, if I have light in water and the imaginary divided with an imaginary line, that water, I will have 100 transmission through it. Of course, there is a special case when I have completely two different media, but with the same refractive index and everything else the same. The light doesn't know. So that's another case. But I call this trivial solution, so this is not interesting. Can we have two different materials, different refractive indices, and have 100% transmission? And the answer is yes, except that it cannot be TE mode. So let's take a look at the TM mode. So remember, TM means your H is like this, and your E is somewhere both in whatever these axes were, Z and the other one. Okay? So here's what happens. If you work this out, you remember we have the n squared in TM, not H, n. And in the denominator you have that difference, right? Something minus something else. Okay, that gives you 0. You have exactly this solution. This is the solution for TM to give you 100% transmission. Okay? So the condition is satisfied simultaneously with the Snell's law, which is this one. If you work that out, something very nice happens. The 100% transmission through the interface happens when, okay, again, this is N1, this is N2. The 100% transmission happens if the transmission, the reflection would happen at 90 degrees. So you use your Snell's law, you adjust your angle until what is supposed to be reflected will be perpendicular to what you put in. If you manage to do that, you get 0 here. You get 100% transmission. Did you get this picture? Theta incident, this one, and theta transmission are such that one plus the other gives you pi over 2. So that means these two are perpendicular. If you manage that condition, that means everything will go through. There will be nothing reflected. Isn't that nice? Yes.
For the transition part.
Uniaxial medium?
Yeah. So in that case, we'll have this reflection for one of the part, not for the other part actually.
Yes.
Right?
Yes.
So if we consider like a circular polarized wave, it will become linear polarized.
Yes, and that's how you can actually play. You have polarization modulators made on this. Yes. Yeah, good observation. Let me give you a picture, a physical picture of why this happens. Do you have a good feeling why this happens exactly when they are perpendicular? Do you know how the dipole radiates? If this is an induced dipole, how does this radiate? So that means, let's say I have a, yeah. In theta, you mean, yes, perpendicular to it will be what? Isotropic. Okay? And then this way will be like a donut, right? Have you seen this before? All of you, right? I'm pretty sure. Let's call it a donut. If you are from Europe, we can call it a bagel. But, okay, so the point is, if I look in this plane perpendicular, I see the same light, or I don't know. It will be the same around this way. There will be zero if I look along the direction of the dipole. Okay, so let's see what that does for us. Well, when my light, this is Tm, keep in mind. So I'm coming in with this K vector. This is the electric field. It's like this. The light we just described in the Lorentz model, the light is exciting dipoles in the medium, right? And basically it's going to shake the atoms in this material along this direction, right? Along the direction of the electric field. So now, if this dipole is exactly parallel to the direction where the reflected light is supposed to come out, it's going to be looking at the dipole along this direction. You'll get zero. Okay, that's why you get zero. Let's pick another angle. If I come in at this angle, and this is the incident, this is my electric field, I'm inducing these dipoles in the material, but my reflection, the reflected wave, is at an angle with respect to the induced dipoles. Then I get some. How much I get depends on the angles, right? We just solved. The Fresnel's equation tells you exactly how much you reflect. But something magic happens when you arrange such that you are perpendicular. So this one comes in at an angle that is exactly perpendicular, is exactly such that the reflected light is along the line of the induced dipoles. So you get dark, you get zero. That's also the reason this only works with Tm. When your H is like this and your E is here. If your E was perpendicular, you see, you always get radiation. You just told me that if I look at this in the plane perpendicular, in the theta you call it, I always get light. That's why there is no Brewster angle when the field is like this. It's only when the field is like this. Are we good? So probably you've heard that Brewster angle, I mean, this was 1850s, something like that. He did a lot of work on polarization as well. You know, these Brewster windows are used in lasers. So you make your laser tube with the windows at a certain angle, and you get linear polarization out. Right? So only Tm comes out with 100% transmission.
Is there
So-
a connection with this and those photonic, bending photonic crystal fibers? Is there any connection?
Bending photonic crystal fibers? You mean polarization maintaining fibers, maybe?
There might not be a connection.
I can make a connection with polarization maintaining fiber if you take it. So when you take a fiber optic and you launch light through it, once you start bending it, there's an effect that actually couples mechanical stress, the fact that you're bending something, to optical properties. So the material, the glass the fiber is made of, becomes anisotropic. And you start with this polarization, which is nice and linear, and you end up with a mess at the other end. The reason being that this polarization splits the is like going through a uniaxial crystal just because you bend the fiber. There is mechanical stress that converts into optical anisotropy. So polarization maintaining fibers are built from anisotropic material that compensates for that. What you give up is now the fact that you have to inject the polarization exactly at the precise angle, otherwise it doesn't work. Okay, so basically you have a fiber, it's made of anisotropic material that compensates for these potential stresses in the fiber. Okay, let's move on. There we go. So this is a more serious treatment of the Lorentz model. We did up to here. This is how you go to optics. Okay? So let me see. Let's establish a goal. Man. Okay. Okay, let's take a break. This is going a little bit more seriously back to the Lorentz model. The reason we're repeating itself is because I used the linear systems applied to the Lorentz model to make it more physical in the beginning. So now we go back and we analyze a little bit the line shapes and dispersion relations that we get from this very simple model. So if you remember, we had an equation of motion, and x2 dots becomes minus omega squared in the frequency domain. X dot with the gamma becomes I omega. And we solved this in the morning, basically like this, very simply. So at each frequency omega, this will be the displacement. If the resonant of the atom is omega naught, and the incident field at frequency omega is this is the mass of the electron, this is the charge of the electron, these are universal constants. The material property is really gamma and omega naught. Omega naught gives you the resonant frequency. Gamma gives you the damping. Something to do with the conduction, right? So high gamma for metals, negligible gamma for dielectrics, glass, and so on. Okay? So I was telling you that that's nice, but that's still mechanics. Where's the optics? Well, in order to get the optics, you need to do the following. The way light interacts with matter is the way we explained for the Brewster angle. I have an incident field. The electric field oscillates, let's say, this way. It's going to generate displacements. Thank you. It's going to generate displacements in the electric charge. So simply the electrons are going to be shaken from their equilibrium position. And this is a dipole that now irradiates.